Hello there, welcome to another problem session. So today we have a really an interesting problem. It's not very hard to do if you have been following Faraday law the way I do Faraday law problems. So here is a expression, a simple statement that we have a circuit like this, and you can just kind of ignore for the moment. You can ignore these connections for the moment. Okay, so you can see the circuit is just this, and inside a space between circuit you can have a solenoid coming out. So circuit is this way and solenoids come out. So if you look in 3 dimension, this will look like a solenoid. This will look like a solenoid, this middle part, and the circuit will be like that. So solenoid is coming out like that, so it's surrounding the solenoid. And so you have a here and point B here, and you want to know what's the voltage across those points are. So you take a voltmeter and you attach A and B. Another you can do 2 voltmeters. You can do this voltmeter and then move it over on the other side. You can do either way. And because this voltmeter is going to be ideal, and so they don't no current will flow through the voltmeter. Of course, very minuscule amount of current has to flow. Okay, so but we can ignore that current. All right, so we're supposed to find what's the reading when the voltmeter is on this side versus when the voltmeter is this side. And surprising fact is, if this current in the solenoid is changing, so as the flux is changing, causing rate of flux change equals to some constant alpha. Okay, so if the flux inside here is alpha of t, and outside the magnetic field is 0, B equal to 0, B equal to 0, B equal to 0 here. So those other areas all B equal to 0. Then what you're going to find is that voltage on the left side, if you place the voltmeter on the left side, is different, reads different than the voltage read when you place it on the right side. And this is a big surprise, and a lot of people don't believe. You have to set this up in the lab for you to actually maybe believe it, unless you are a big theory person and you really are convinced about the theories and you like the math, and then you say, okay, whatever the math says has to be in the lab. But it is a counterintuitive. Usually when you do DC circuit, the voltage between 2 points doesn't matter where you place the voltmeter. It's going to have same reading. But here, surprisingly, you have a different reading. And that because you have to obey Faraday law. That's the main thing. Every loop that you go, physical or mathematical loop, you go in space, it has to be E dot dl integrated in the loop has to be equal to rate at which the flux changing through that loop. Okay. Having said that, because this problem is a little confusing, I'm going to give you the answer, and you can try it out and see if you get the answer. Set it up, Faraday law, and so I'll give you a hint. You can set the Faraday law for this. That will give you the current in this circuit containing R1 and R2, and then you can do this loop to find the voltage reading for this, and then you can do this loop for voltage. You can do any loop to get the voltage reading, right? You can go this big loop, and then you have to worry about including the magnetic flux. So we can do I'm going to do all the loops, and then we're going to have a full understanding of why this happens. Okay, Having said that, try to solve this problem on your own, and then you can come back. Okay, so I'm going to do circuit A, B, capital B, C, D, A. So I'm going to go around. So I'm going like this. I'm going to go in this direction. So this is my DL direction, and so the n hat direction is going to be coming out like that. And that turns out is exactly opposite of that. So that means B dot n hat dA over this surface will be negative of what was over there, because this is normal is down in, the normal is out. So this will equal to minus alpha t. Okay, so we have EMF equals to minus EDL equals to ddt of, so this is the phi b for this loop. So this is minus alpha t. So this just turns out to be minus alpha. So EMF is minus alpha. So you can see that so E dot dl is alpha here for this loop in this orientation. So the current is in the same direction as this, because this is positive, this is positive, so this is positive. So that just means the current is all is that way, and the current induced is that way in this circuit. Okay, so now we know the current is going this way here, and the current is going this way here. And the current amount, how much is the current induced, is going to be how much EMF is divided by the total resistance in the circuit. So it's a series circuit, so it's going to be R1 plus R2. So it's alpha over R1 plus R2. Okay, so that's the part one, to get the current and the direction of the current. And so now we are in a situation to actually work with what the voltage reading will be on the two sides. Okay, so let's see on the left side. So I'm going to do, this is the voltmeter, and this side is the plus orientation voltmeter. So R1, and the current here I induced is this way, and I here is 0. So if I go in this loop, let's see, we go, if you go from here to there, say this is going to DL, I go like that for DL. So this is DL here, and DL is that way here. Okay, so I'm going to go from E to A to B and back to F. So if I do this out, now here there is no magnetic flux going through here, so you can just do V equals IR, so if you can see if the current is going this way, then this minus this at a higher voltage, and this lower. So this is because there's no magnetic flux through this changing magnetic flux. So this is the old thing. So this is just So this will have a positive reading and this will be a negative reading. So this is going to be plus I induced times R1, and it's going to be plus, and so this is going to be alpha R1 over R1 plus R2. You say, so this will be reading, okay? So VE minus VE minus VF will be just this, because you can say you go whichever ways. It's going to be just this high voltage, this is the lower voltage, and then just work it out like that. Okay, could we have gotten this if I had another loop? Like suppose I took this loop. Sure, should get the same answer, right? Okay, so we go in this circuit in a different way, in a different loop. So we're gonna go in this loop like that. So this is my DL, and so that's DL is opposite to I end here, and there will be alpha going in the same direction as that. So the dB dt, is changing over here in the same way. So that's phi b will just going to be down. If you going right hand, it's just going to go inside. So this is alpha it is pointed down. Okay, so let's do it. And so I get E dot dl should be equals minus d dt phi, and this is the only, and outside here is b is 0, so this is the only place that the b phi b matters in the whole loop. So we're interested in phi b for this whole thing, but this is the only place that's going to be non-zero. So the right side is going to be minus d dt, and the orientation that I'm going in the loop is the same orientation as that. So this is going to be just alpha t, not like before, minus alpha t. And this side will be A to D, nothing will be there, no resistance there. So from here to here, it's going to be minus D to C E dot dl. This is going to be plus, I'm using plus minuses on the other side. Then we have a plus C B, nothing happens over, and then over here is F and E. That's the only place is gonna have matter. So F to E dot dl, and everywhere else is 0 plus 0, plus 0, and that's equal to minus alpha. Now this, I'm going in that direction and current is flowing in that direction, so I'm going to get a minus I induced, and this resistance is R2, so it's going to be R2, and this is the definition of voltage drop across here with a minus sign. That's going to be the reading of V1, and this is going to be minus alpha. So let's simplify it. I get a V1 equals to alpha minus R2, and so if I write this guy in from before, we already had found this guy was this stuff from before, so there's going to be alpha minus alpha over R1 plus R2, and so this is going to simplify to same as answer before, alpha R1 over R1 plus R2. That's going to simplify to that. It's the same answer as that. So whether I just use this loop with no B here, I use this bit bigger loop with a B there, as long as I set up the Ampere's law correctly, I mean not Ampere's but Faraday law correctly, I'm fine. I get the same answer, right? How about let's try to do the other one. Okay. Okay, so we're gonna do the simpler loop, A to D to B. See, this is R2, and this is the direction in which induced current is. And then reading will be V2, and this is the plus side, this is the minus side. So if I go from here to here, so let's try to go this way. So that will be reading V2, and when I go V2 minus, so E dot dl equals to minus ddt phi b, and this is 0. And so if I go from here to here, that gives you minus V2, and then I go from here, so dl is this way, and so it's going to give me a minus times another minus, right? So it's going to give me, if I have a minus here and a plus here, so I'm going to get a plus, and then I'm going to get a plus. So this both of them will be plus. So, or you can have both of them minus. So over here, there's going to be I induced times R2, and the right side is 0. Either use that, or you can say there's no B here, though no B here. So I want to know what's the voltage here versus voltage here. So from that perspective, the current is going, so this side is higher voltage, and this is the low voltage. So and this reads VA minus VB. That's going to be minus I induced R2. Just from that, or you can use Faraday law and realize this is going to be 0. So it's going to get same V2 reading will be minus I induced R2. So both of these are the same, minus this is alpha over R1 plus R2. Okay, and times R2. So that's how you got it. Okay, so I'm going to leave that as an exercise for you. Try to see if you get the same answer in this loop. Okay, that's a good practice for you. It's a really good problem. So you learn a lot by doing this. Although it comes from a little bit advanced book, but it is actually an introductory physics level problem. It's just confusing that the voltmeter on this side reads 1 and voltmeter placed on the other side reads another. That has to do with the circuit being dynamic, and there is a changing magnetic flux inside the loop. All right. Now you like this kind of problems, you can check out more over here, and you can subscribe to this channel. That helps grow the channel. You can that also helps spread the word. You can talk to your friends, maybe you can tell your teacher about this channel. It's all in all is a good thing. Thank you, take care, and bye.